Strong bases. So a strong base is one that dissociates completely in solution. And we end up with the hydroxide ion concentration being equal to the concentration of the base, because it completely dissociates. Most of the strong bases are either group 1A or group 2A metal hydroxides. So we've got lithium hydroxide, sodium hydroxide, potassium hydroxide. Those are group 1A. Here's group 2A, strontium, calcium, and barium hydroxides. Now, these are going to give us 2 moles of hydroxide for every 1 mole of the base. So these group 1A metal hydroxides, these are very soluble in water. So we can make quite concentrated basic solutions. The group 2A metal hydroxides are only slightly soluble. They do produce 2 moles of hydroxide per mole of base. And unlike a diprotic acid, which dissociates and gives off 1 proton at a time in separate steps, these they give up all their hydroxides at the same time. So strontium hydroxide will dissociate into strontium ions and 2 hydroxide ions. But they're only slightly soluble, so these group 2A metal hydroxides, you can't make real strong solutions out of them, concentrated strong. Weak bases. So weak bases are like weak acids. The most common weak bases are going to produce hydroxide by accepting a proton from water instead of the ionic compound that's actually adding hydroxide ions. So we can use B to represent a generic weak base. So the base interacts with water. Bases accept protons, so it takes a proton from the water, leaving hydroxide. Ammonia is probably the best known weak base. So here we've got NH3. Ammonia reacts with water, takes on the proton from water and hydroxide. Sometimes this is referred to a solution of ammonium hydroxide, but it's really aqueous ammonia. That's what it does. So we have, instead of an acid ionization constant, we have a base ionization constant, so that's Kb. And this tells us how strong the weak base is. So we look at this reaction where the base is accepting a hydrogen ion and forming hydroxide. Kb equals the concentration of BH plus times OH minus over the concentration of B. So if you have a small Kb, that means you have a lower concentration of products. It's a weaker base. The higher value of Kb means it's a stronger base. It says acid. Yep. I can fix that. There we go. Smaller Kb means a weaker base. And we can calculate pKb in the same way that we did pH and pKa, negative log of that constant. So here's a table from your book of some common weak bases. Gives you the ionization reactions. Here's the Kb, base ionization constant, at room temperature. You might need to look stuff up there. A lot of the weak bases are amines. Those are organic compounds. But we can think of them without getting into OChem as ammonia with things substituted in for the hydrogens. So here you have ammonia, right, NH3. This is an amine where we have this methyl group, a carbon with hydrogens on it, substituted in for this hydrogen. So amines are very much like ammonia. They just have other things attached to the nitrogen instead of just hydrogens. And they act as a base in the same way that lone pair of electrons on the nitrogen is what can accept the proton from the water molecule. So here we also have that lone pair of electrons on the nitrogen, and it can do the same thing. Finding hydroxide ion concentrations and pH for these basic solutions. With the strong bases, we don't need to think about the autoionization of water because it's negligible. When we're looking at weak bases, it's very similar to doing the weak acids. We're going to neglect the contribution from water. We're going to make an ice table, and we're going to use the Kb expression to find hydroxide ion concentration. So let's do an example. This is a strong base. Find the hydroxide ion concentration and the pH of a 0.010 molar barium hydroxide solution. So they didn't give us a Kb, did they? They didn't give us a Kb because there isn't one. This is a strong base. How do you know that? Metal hydroxide, where the metals in group 1A or group 2A. So we have BaOH2, and that's going to dissociate and form barium ions and hydroxide ions. And we're going to get 2 moles of hydroxide ions for every 1 mole of barium hydroxide. So if I'm starting with 0.010 molar barium hydroxide and all of it dissociates, then I'm going to end up with 0.010 molar barium ion and 2 times that for the hydroxide ion. You can write that out in different ways. That's not something that I really think we need to really show our work for. It's a base with 2 hydroxides, and so the hydroxide concentration is twice that of the original substance. So hydroxide ion concentration is going to be 0.020 molar. It wants the pH. We have the hydroxide ion concentrations. Do you remember the circle of pH? We want to get to pH from OH minus. We can take OH minus and change it into hydrogen ion concentration and then pH. Or we can go from hydroxide ion concentration to POH and then to pH. That's what I prefer to do. So POH is negative log of 0.020. So that is 1.70. pH is going to equal 14 minus that. .30. That's the pH. Any questions?
So basically, if it's already in OH form like that, and you find you have morality of the OH, when you negative log it, it'll give you the POH.
Mm-hmm.
But if it was an H, it'll give you the pH of it.
Yeah, if we've got, if the concentration is hydrogen ion, then we get pH. If it's hydroxide ion, we get POH. You can also do things like calcium ion, then you get PCA. You can take the negative log of your ionization constant, the Ka, and then you get pKa.
Quick question.
Yeah.
You said that Kb is only for weak acid?
Mm-hmm.
And that's because it's strong acid completely.
Yeah, a strong acid or a strong base will dissociate completely. And so you would have concentration of the products and essentially none of the reactant. And so it's either going to be a ginormously huge number or undefined because the denominator is 0. So there's no point in even talking about it, yeah. So let's do it for a weak base. So here we have 0.33 molar methylamine solution. So how do you know that's a base? Well, if it has amine in the name, that's a big clue. It's probably a weak base. Over here, we've got Kb being given to us. That probably means it's a weak base, right? Because if it was an acid, it would probably be giving us a Ka, and the name would have acid in it. So yeah, I don't expect you to know how to draw the formula for methylamine or anything like that. So how are we going to represent that? Well, let's just call it B. B for base. So our base plus water is going to be in equilibrium with the conjugate acid, BH plus OH minus. Water is a liquid, and so that does not come into the calculations. So we're going to do an ice table here. The initial concentration of the base was 0.33, and the initial concentration of BH plus would be 0, because it hasn't had a chance to do anything yet. And the hydroxide ion concentration, the only thing present would be from the autoionization of water, and we're going to assume that that's so small it doesn't matter. So that's 0. So then for change, this is going to decrease, this is going to increase, this is going to increase, and that's all the x's again. So 0.33 minus x, x, and x. So the base ionization constant, 4.4 times 10 to the minus 4, equals those products, x and x, which is x squared, divided by 0.33 minus x. This is a fairly small Kb, so we'll try the x is small approximation. In that case, x will be equal to the square root of 4.4 times 10 to the minus 4 times 0.33. I'm just rearranging this equation. I'm leaving out this minus x because that's what x is small says. So x is 0.012. I'm going to check that, divide it by the number I'm subtracting it from. So divide by 0.33, multiply by 100, 3.7%. X is small, approximation is valid. Okay, so we calculated x. What were we trying to find again? We wanted the hydroxide ion concentration. Well, in our ice table here, the hydroxide ion concentration was equal to x. So we have one of our answers, hydroxide ion concentration equals 0.012 molar. And then they want the pH. So find the pOH and subtract it from 14. So this is the negative log of the thing we just found. .92. So pH equals 14 minus 1.92, 12.08. What's the pH? Is that a reasonable pH? It does seem kind of high for a weak base, but look at the concentration. 0.33 molar is actually pretty high. And the thing about the pH is if you don't have any sort of a buffer in there, it doesn't take much to make the pH change a lot. Any questions?